Hello, today we are going to discuss the network theorem, which is a part of same 2 physics honors syllabus, paper 3 electricity and magnetism. And in the network theorem, we'll discuss superposition theorem, reciprocity theorem, Norton theorem, Thevenin's theorem, and maximum power transfer theorem. So before moving on to the theorem part, we'll discuss in brief about the ideal voltage source. Now here what we have mentioned is that it is an active device which can maintain a constant voltage across its terminal irrespective of the current supplied by it. It is now called it is also called rather a constant voltage source. Okay, so you should have an idea about this thing. It's very important before moving on to solving this network theorem. Then we have a constant current source. Okay, again it is an active device which can supply the constant current to any load resistance, and okay, that is connected across its terminal. So these are the two things which you should have an idea about. In the case of the ideal ideal voltage source, okay, it is always equal to open circuit voltage. Okay, now in an actual voltage source, the voltage across its terminal decreases at the load as the load resistance is decreased. Okay, now in the case of a constant current source, which we have mentioned over here, okay, the terminal voltage is directly proportional to the load resistance. Okay, so it is the terminal voltage is directly proportional to the load resistance. Now we'll just come on to the theorem part. Now these two parts are very important, that is ideal voltage source and the constant current source. Now regarding superposition theorem, what we know is that in any linear network consisting of linear impedance and potential across the current flowing in any element is the phasor sum of the current that would flow in that element by each potential source. So all the other sources being replaced that time by their internal impedance. Now this could be understood by just considering an example. We'll try to solve it. I've just made a small circuit for that. Now here what we'll do is that we'll just focus on this particular circuit. Here we have considered a case of network consisting of two meshes, mesh 1 and mesh 2, okay, with two potential sources E1 and E2, okay, with internal impedance Z01 and Z02. Now there is a current over here, you can see I1 and I2. So we are having current over here as I1 and I2 rather. Okay, there is no prime sign over here. Now you can see over here we are having two sources, E1 with internal impedance Z1 and E2 with the impedance this much. Okay, again we'll consider, we just modify this particular mesh. We'll have Z1 over here, Z3 over here, again I1 prime. Okay, in this particular case we'll have I1 prime and again Z2 over here. Okay, in place of this E2 we'll have we'll have Z02. Okay, so in this case we have again we have to take like this. Okay, here also we just have a current over here, that is I1 prime. Okay, already I have taken I1 prime, and here we have I2 prime. This is one of the situation. Another situation is like if we remove this I1 or rather I1 over from here, then we'll have Z1 and obviously Z2 will be there. Okay, the source E2 will be there. Okay, with the internal impedance Z02, and obviously Z3 will be here, and here we have only the internal impedance Z01. Okay, so Z1 is here, Z2 is here. In this particular case, again we have the current I1 double prime, and here we'll have I2 double prime. Okay, now no, all of us, we have the basic idea of the Cramer's rule. Okay, so we'll use that one, and we'll also use Maxwell's relation or Maxwell's law rather in this particular mesh to solve this equation. I mean, to find out to prove the theorem rather. So we'll write here E1 equal to Z1 plus Z3 plus ZO1, okay, into I1 plus Z3 I2. Here we have taken this particular mesh, and then again E2 equal to will have Z3 I1 plus Z2 plus Z3 plus ZO2 into I2. Rather, we have taken the first one, okay, so not this one. We have considered the first mesh, this one. So we'll take an I1, I2. While writing this particular equation, what we have done is that E1, okay, so E1 is equal to, we'll consider this first mesh, okay, so we'll have Z1 plus Z3 plus Z01, okay, Z1 plus Z3 plus Z1 with I1 and plus Z3, so Z3 I2, and further for this particular loop, I mean, here we have E2 equal to Z3 I1, okay, Z3 I1 plus Z2 plus Z3 plus Z02 into I2. So these are the two equations, okay. Now using Maxwell's method, we can write here I1 equal to, it's very simple. What we do is that what we have done earlier in determinant also, we have applied, we know the basic idea of the Cramer's source, so you can take the help of that. I1 is equal to E1 E2, okay, and you will write Z3 Z2 plus Z3 plus ZO2 by the whole of this thing, okay, the coefficient of I1, okay, again the coefficient of I1 here is Z3, okay, and then the coefficient of I2 is Z3 Z2 plus Z3 plus ZO2. So this is what we'll write. Okay, so from here what we'll do, we'll just represent this one by delta Z. So ultimately we'll have I1 equal to, if we'll expand this one, we'll have E1 Z2 plus Z3 plus ZO2 minus E2 Z3 by delta Z. The delta Z is equal to this much, and I2 equal to, again we'll write minus Z3 I1 minus Z3 E1 plus Z1 plus Z3 plus ZO1 into E2 by delta Z. So similarly, rather, as we have find out I1, we can easily find out value of E2. In the case of E2, what you have to do to find out E2, what you'll have to do is that you'll again have to put the value of the corresponding value of in the place of E2, okay, you'll have to put E1 and E2 over here, and the Z1, Z2, Z3 and this one Z3, and then you'll go and solve this thing, you'll get the same thing. So this is what you'll get. So I think it has to be very clear now. So now to prove superposition theorem, what we do is that we first find I1 prime from here, I1 prime, okay, and I2 prime by short circuiting. What we have done is that we have short circuited, okay, there is only ZO2, there is no E2 over here. So we have short circuited this one, and then I1 dash double prime and I2 double prime by short circuiting EMF E1. So using the two figure, this and this, okay, we'll have I1 prime is equal to Z2 plus Z3 plus ZO2 into E1 by delta Z, and I2 prime will be equal to this will be equal to minus Z3 E1 by delta Z. Okay, so this what we will have I1 prime and how to find this I1 prime, so what we have done is that we have assumed E2, in this particular case E2 to be 0. So you can do one thing, you'll substitute E2 over here 0, ultimately you'll get this particular relation. Okay, I1 prime and I2 prime from these two equations. Okay, you substitute E1 and E2 0. Okay, in this two equation you get this one, I1 prime and I2 prime. Finally, again, using the same two equations, we'll put initially what we done is that we have put E2 equal to, so we'll put E1 equal to 0, and then we'll get I1 double prime equal to minus Z3 E2 by delta Z, and E2 double prime equal to Z1 plus Z3 plus Z01 into E2 by delta Z. Okay, so solving these two, we'll have I1 equal to I1 prime plus I1 double prime and I2 equal to I2 prime plus I2 double prime. This can be done by you also. So thus we have proved the superposition theorem, and this particular theorem, it can also be used if voltages of different frequencies are introduced. Not only this, if we will use the voltage of different frequency, that can also be proved over here. So see, because of this, already I have used 11 minutes for this particular part of this network theorem. So I think it will be better if I will continue the next theorem, that is the reciprocity theorem and the Thevenin's theorem, in the next lecture. So it will take at least 3 lectures to be done of 12 minutes each to complete this all the network theorem. So let's again for the reciprocity theorem and Thevenin's theorem I will discuss in the next chapter, next lecture. Thank you.